I made a simulation of a water fountain in order to answer an important question: how the velocity with which the water is ejected is related to the area that gets wet. Here is an example. If we know the area that gets wet, can we figure out the velocity with which the water is ejected? In order to answer that question, let's focus on a single stream of water. Let's say it's emitted with speed u, angle theta, and covers a horizontal distance x. Now let's apply a kinematic equation on the motion. The equation I'm looking at is S equals ut plus 1/2 at square. I want to use this equation on the vertical axis. So we should modify our equation accordingly. Let's apply this equation between 2 points, one, the start of the motion, and the other one at the end of the motion. If that's the case, the displacement is 0 and the acceleration is minus g. Why is displacement 0? Well, simply because the initial and final vertical distance is the same, that is 0. In gravity, points downwards, hence minus g. If we substitute these values back into the equation, we'll get 0 equals ut minus half gt square. This equation can be rearranged for uy. Let's do that. If we do that, our equation becomes uy equals half gt. Now let's make t the subject. T turns out to be twice uy over g. But we want to relate uy to u and theta. In order to do that, let's look at the components of the initial velocity vector u. We can break u into two parts, ux and uy, with the horizontal part being u cos theta, the vertical being u sin theta. So if I substitute the value of uy into the t equation, I'll get t equals 2u sin theta over g. This completes the first part of the problem. We know the time it takes for the projectile to land back on the ground. Now let's look at the projectile from another angle. If you look closely, you'll find that the horizontal velocity always stays constant. This means that the horizontal distance covered by the projectile would simply be the horizontal velocity times time, with the horizontal velocity being u cos theta. The equation for area that gets wetted is pi r square. We can substitute the value of r into the area equation, which gives us A equals u cos theta t squared. But wait, we already know the equation for t. Now let's substitute the value of t back into the equation for the area. If I do that, the equation we'll get is shown here. Now this equation can be simplified by some algebra, and we can get an expression for u. If I take a fourth root both sides, we get the required equation for u. That is shown here. And that completes the problem.